Everyone, welcome to the August LOF&BE webinar series. I'm Sarah McAllister. I host these with Dr. Sam Manzello and Sayaka Suzuki. We've got two student speakers today. The first is Ting Xia, and I'll let her get started. Thank you.
Hello everyone, my name is Ting Xia, and I'm very glad to have this opportunity of presenting the results of our team. Today, I'd like to give a brief introduction to informal settlements in China. My presentation will include the types of Chinese informal settlements, ethnic minority traditional settlements, two case studies in Southwest China, and a brief summary. In the first part, I will talk about the types of Chinese informal settlements. As we all know, in Africa, there are many informal settlements like slums, shacks, and there have some fire research about this issue. While in China, there are also many informal settlements, and in this place, fire often occurred. But the fire research is very limited. So in order to the last one is ethnic minority traditional settlement. These settlements are the history and the culture of the Chinese ethnic minorities, and their dwellings often made of local materials such as timber, bamboo, thatch, and stone. Most of these are combustible. Well, they often located in mountainous area, so it's very difficult for the fire rescues. And we also collected the number of ethnic minority traditional settlements in the whole China, and this is the distribution for every province. And we can find that in Guizhou, Yunnan, Sichuan, the population of the number is very huge. So next part, so we analyzed the numbers of these settlements in the Southwest China in detail. Well, during the investigation, we found that the fire often occurred in this place, and in past 20 years, there have been 18 traditional settlements fire occurred. So in order to better understand this kind of informal settlements, we investigate the ethnic minority traditional settlements in detail. According to the National Ethnic Affairs Commission, there are 1,244 settlements in Southwest China in total, but the document only have the name of these settlements, so we investigate the information one by one, and including the minority type, structural characteristics, building materials, slope, and latitude, and these are the results. For the minority type, there are over 60 types of ethnic minority, and for each minority, they have their own traditional building. For example, the steel building, bamboo building, and for all these buildings, they have the structural characteristics, and we found that the steel building is the most common structure. We also investigate the construction material, and it was found that wood is usually used as the building material for these settlements. What's more, as these settlements often located in mountainous areas, so they are often with large slope and high latitude. The average slope of these settlements is 20 degrees, and the average latitude of these settlements is 1,136 meters. From the above investigation, we can find that the dwelling itself is combustible, and there are many complex environmental factors, such as low latitude or wind, that will also influence the fire behavior. So to better understand the fire in these settlements, we then conduct two case studies in the Southwest China in these settlements. The first one is Wonding Fire. Wonding village is the last primitive tribe in China, and in this fire, almost all houses were destroyed. And the second one is Shangri-La fire. Shangri-La has a long history of over 1,300 years, and it is the best preserved Tibetan settlement in China. In this fire, there are 343 houses were destroyed, and the direct economic damage is about $14 million US. Then we analyze the influencing factor of fire by geographic information systems. And firstly, we analyze the household proximity. It is an important factor for the fire spread. And these are the satellite images of Wonding and Shangri-La. In order to calculate the household proximity, we vectorize these images and buffer these vectorized images to calculate the proximity. We can find that the distance for the fire spread of Wonding is 8 meters, and the critical distance for fire spread in Shangri-La is 3.3 meters. In addition, in order to find out the areas with fire risk in these villages, we also use the vectorized images to create the near table. In this table, we calculate the nearest neighbor and the range from the first to third nearest neighbor. And in these two pictures, the range is vectorized as the circles. The big circle means the range is low, and the nearest neighbor is vectorized as the color of this house. So if the building is red, that means the first nearest neighbor is low. And then combine these two factors, we found that the fire risk of Shangri-La is higher than that of Wonding. What's more, the slope is also an important factor to affect the fire spread. So firstly, the satellite images of these two villages and their corresponding original DM data are extracted by the mask to obtain the DM data. Then we conduct the slope analysis and the classification of slope. Then we obtain the corresponding slope data. It was found that in all these two areas, most of the areas, the slope gradient are within 8.5 degrees. Then for the latitude analysis, we also use this obtain the DM data to extract contours and visualize them to the corresponding latitude. It was found that the latitude of Wonding is about 1,493 meters, and for Shangri-La, the latitude is 3,265 meters. The arrival time of the firefighters is also a key factor in the fire rescues. Thus, firstly, we create the road network dataset and then determine the location of the Wonding village and its nearby fire stations. Then, through the network analysis, we calculate the time required for the fire stations to the Wonding village. And for the one road, it needs 40 million, and for another station, it needs 38 million. And the same for Shangri-La, it also needs about 15 million for the fire bridge to get to the fire station in Shangri-La. In these two pictures, we can see that the roads in these two villages are very narrow, so it is very difficult for the fire engines to enter these fire scenes. Then I'll give a brief summary. Firstly, we summarize the types and the fire hazards of Chinese informal settlements. Then we investigate the characteristics of ethnic minority traditional settlements including the minority type, structure, characteristics, building materials, slope, and the latitude. Finally, we analyzed the influencing factor of fire spread in these two case studies, and we found that the critical distance for fire spread in Longding village is 8 meters, and in Shangri-La is 3.3 meters. What's more, the fire rescues and the firefighting facilities are very important in this kind of fire. For the above research, I greatly appreciate my supervisor Yuan for the guidance of this research, and also appreciate Li for the content with GIS analyzed. And thanks very much for the technical support provided by Leslie. In addition, we really appreciate these funds for the support of the research. And that's all for my presentation. Thanks for your listening to me. Any questions?
Thank you. That was a fascinating summary of all the different varieties of settlements in China. I had no idea there was such a wide spread of, especially the traditional building styles and everything. We had a question in the chat box here for you. So thank you very much for the presentation. Can you tell the difference between traditional settlements and historical sites?
Oh, well, we analyzed the traditional settlements, and these settlements are have a great cultural value for the Chinese ethnic minorities, and not all of these are historical sites. As we know, the traditional settlements, there have many residents in these settlements, but for the heritage building, these are not all for the human behavior to living there, and some of them just for the visiting. So these two kind of building not equal.
I gotcha. That makes total sense. While waiting for another question, you can always unmute and turn your camera on and ask questions at any time. Another one in the chat box. So on your slide 21, they would like to know how you chose the buffer distance.
Oh, well, firstly, this research is based on the informal settlements in South Africa, because they already have some research. So we found that in South Africa, the critical distance for fire spread is 3.3 meters, and then we use this distance to analyze these two villages. We found that for Shangri-La, the 3.3 meter can make the fire spread, but for Longding village, 3.3 meter is too small to fire spread. So we further analyzed the critical distance, and then we found that when the buffer distance was set at 4, these areas can overlap. So the critical distance we can find is the double for, so it is 8 meters for the fire spread.
Which I thought was really interesting. And you showed pictures of the two settlements and like the way that those buildings were built, like very different construction. Do you think like the construction type influenced that? I mean, versus like the straw roofs versus the wood roofs, did that come into play, you think, in that critical distance?
Well, these two settlements, their building are really different, and maybe they are similar and they are both combustible. But for the villages in Longding, there are on the top of the house there are some slash, and for the Shangri-La there are almost all timber. That's the difference for the building materials, and actually there are many structures are different, and so we just analyzed these settlements fire from a very large scale. So we didn't just analyze for the single derailing, but as we can see from this analyze the slope and the latitude also different for these two segments. So all of this will influence the fire spread, and also the wind will influence it.
Yeah, that's a good point. That's true. Another question in the chat box is, have you compared the fire spread mechanisms between these settlements and those in, say, South Africa?
Oh, yeah, we have done some comparisons, but not present in this presentation. Well, in South Africa, as we all know, most of the materials are the sheets, and they are not combustible but very easy to qualifies, and the most important issue for the bonding materials of the South African informal settlements, they have leakage, and so their boundary conditions is very different. But for these settlements in China, the most important issue is that they are all combustible, and they also, you can see from the pictures, they're located in the mountains, and so the slope will influence the fire spread to another place, and also it is similar, some way is similar to the forest fire. But for the informal settlements in Africa, well, the analysis for this environmental factor of the fire spread is not so. It's not to be understand.
Gotcha. Again, that makes very much sense. Thank you. Sam, also, again, thank you for a great talk. Well, if anybody else has any questions, feel free to speak up, type them in. We'll give you a minute or two, and then we'll move to our other speaker. Maybe in the meantime, if you want to share your screen, Amila, and
yes.
Thank you, transition.
So, yeah.
All right.
Okay, I'm going to share my screen.
So our next speaker is Amila Wickramsinghe. Hopefully that was close.
Yeah.
He's a PhD student at Victoria University in Australia. So I'll let him get going.
Yes, thank you, Sarah, and thank you everyone for attending today's session. Okay. The presentation title is Determining Fibrant Generation Rates Using Physics-Based Modeling. So I'm going to present some findings of my PhD research project, which was supervised by Professor Khalid Mohiuddin, Dr. Nasmul Khan, and Dr. Alexander Filkov. A little bit about myself. I'm a PhD candidate at Victoria University in Australia, and I graduated as a chemical and process engineer from University of Mount in Sri Lanka. After graduating, I worked in different industries and different disciplines such as power generation, textile, and wind farm modeling. And right now I'm in the fire modeling section. The outline of the presentation can be presented as here. First, I'm going to talk about wildfires and the structure ignition mechanisms. Then I will give a little brief about fire brands and how it's important to quantify the fire brand duration. Then I will be talking about physics-based modeling and the tools that we used in our project. Then later on, I will be talked about modeling of laboratory and field scale experiments using these tools. Later, I'm going to talk about the calibration of fire brand duration. And at the end, I will be finished this presentation by quantifying the fire brand attack on houses and how important our findings for regulating the building standards in wild and urban interface. So yes, we all know wildfires are dangerous, and it's considered as a powerful dynamic ecological phenomena that can take place in bushfire prone areas for centuries. And there are natural causes and human activities that can initiate wildfires. For instance, lightning strikes, sparks from falling rocks, and volcanic activities can be classified as natural causes, while campfires, deliberate fires, and even sometimes the sparks from machineries like movers, chainsaws, grinders can cause a destructive wildfires in the wild and urban interface. So talking about wildfires, we need to talk about wild and urban interface because for past 2-3 decades, we can see there's a huge increment of wildfire initiation in this region. So wild and urban interface identified as the region where houses intermingle or meet the undeveloped wildland vegetation. So we can see a lot of destructive wildfires happening in this region right now. So these destructive wildfires can cause fatalities and they destroy our farming lands and cultivation to disturb the sustainable food production. And also it affects for the climate as well. And sometimes we need to have proper strategies and management scale plans to evacuate people and displace them away from the areas that these wildfires can be happen. And the other important thing is damaging houses. These destructive wildfires annually destroyed thousands of houses over the world. And talking about house ignition mechanisms, there are main three mechanisms, which are direct flame contact, radiant heat, and the fire brands. Sometimes a two or all of them can combine together to make a huge destruction or damage to a house. Direct flame contact is identified as when fire flame is impinging on building materials, providing the highest heat flux. And in contrast to that, in radiant heat, the heat is transferred from thermal source to the distance through the air. And depending on the distance, flame length, and the angle, emissing power, and depending on the exposure time, the ignition of houses can be varied. And this is an schematic diagram that you can see here, which shows how the direct flame contact occurs and how radiant heat transfer to the house for ignition and how firebrands are moving towards house blending with the wind field and fire-induced buoyancy. So what are firebrands actually? Firebrands are identified as a small ignitable particles that can be generated from burning vegetations. These particles could be twigs, leaves, cones, or even fragments of barks. The danger is when these small heated up firebrands blend with the wind field, they can fly a long distance until land on a full surface or on a structure. When this happens, there's a possibility to start a new fire, which is called a spot fire. So depending on the distance of firebrand spotting, we can classify them into three separate sections, which are short range spotting, medium range spotting, and long range spotting. So we can see most of the time flat trajectories in short range spotting. There's a little or no lift of firebrands when classifying short range spotting. In contrast to that, we can see firebrands are moving upward with the convective column of fire-induced buoyancy until they carried by the wind field to land on a distance. So in long range spotting, we can see a different kind of a trajectory. And in medium range spotting, we can see both of these combination of short range and long range spotting. Talking about firebrands, studying firebrands is really important, and there are a lot of experimentalists and scholars doing various kind of studies related to firebrands and to identify firebrands characteristics and their nature. There are laboratory experiments and field scale experiments, so I have put some of them here. So you can see there are some experiments done by Samuel Mancero. Samuel is here right now, and Sayaka is also here. So all these laboratory and field experiments are really important to generate some data to use in simulation models. And these are the basic branches of studying firebrands. And firebrand study can be classified into four separate sections, which are firebrand generation, transport, deposition, and secondary ignition. These latter three aspects have been examined extensively in the operational context, but firebrand generation has not. There has been created a gap in this particular field. However, knowing or measuring firebrand generation is not an easy task. We might need to go to Firefront and we need to collect data. And of course, to do that, we need a lot of safety precautions and we may need a lot of advanced instruments and technologies. And of course, we need a lot of financial and human resources. Due to these limitations, there has been created a knowledge gap in this particular field. However, we do have an alternative method to quantify the firebrand duration. We don't need to go to Firefront. That alternative is a viable alternative, which is physics-based modeling. This computational dynamics models solve the governing equations of mass, momentum, and energy numerically. And we can use these physics-based models to investigate different aspects or different branches of fibers. For instance, fiber transport, spotting and distribution, and their pulses and oxidation characteristics. Sometimes we can quantify the effect of size, shapes, and their releasing height for start and ignition and deposition, so on. In this work, we are mainly focused on using physics-based modeling to quantify the firebrand duration rate and subsequently the transport and especially the firebrand attack on houses. When you're using this kind of physics-based model, we need to careful because we need to have proper validations and grid sensitivity analysis to use them in operational context. And also sometimes we need high computational power to simulate these complex cases. In this work, we are using a physics-based model called Fire Dynamics Simulator. It's a product of National Institute for Standards and Technology in USA, and it's a computational fluid dynamics-based model. And this model solves the governing equations of fire-driven fluid flows numerically. And this is an open source software, so we can download the source code free of charge from the internet and implement according to our objectives. So we did the same thing in this work as well. So in our work, we do have 4 phases, and we are starting with the simplest case, which is try to quantify the firebrand duration rate in a single burning tree. With that findings, we're trying to expand that further into find the firebrand duration of a cluster of tree burning, or we can call it as a forest fire. So these findings will be used in the third phase for calibration of firebrand duration based on species, wind and fuel moisture content. To do that, we use some other experimentalist data. And at the last phase, we are going to map the firebrand and heat flux on structures to appraise the Australian standard document AS 3959. So AS 3959 is the prescription of constructing buildings in bushfire prone areas in Australia. So starting with the first phase, we try to model a single burning tree. So in this case, we associate with one of our laboratory scale experiment conducted in National Institute for Standards and Technology. So Sam is here. Sam and his team is the people who did this great experiment. They have burned series of Douglas fir and Korean pine trees and collect various kind of data about firebrands. We took one of the experiment. This is a Douglas fir tree burning experiment. And from this experiment, Sam and his team, they have collected a portion of generated number of firebrands, placing some water-filled trays around this tree base. And also, meantime, they have measured the dimension of the tree, the fuel load, and the fuel particles dimension, and the mass loss rate against the time. So we do have that data. So we are going to model that using fire dynamics simulator. First, we maintain the bulk density, fuel moisture content, physical dimension of the tree, and the fuel particles, same as the experiment. So we received the firebrand data, the collected firebrand data, like mass of the firebrand, number of firebrands, and their dimension from Samuels and his team, and we processed them to use as inputs in our model. First thing that we did was we validated the pyrolysis and the combustion in terms of mass loss rate against the experiment. So this is the comparison of mass loss rate between the experiment and simulation. As you can see, the nature is pretty much similar. There's only a 6% difference for total mass loss. And by doing so, we could ensure that the burning characteristics or burning nature of the simulation and the experiments are pretty much similar. Then we carried out an inverse analysis process to find the firebrand initial velocity and the duration rate. So what is actually inverse analysis technique? In this case, what we did was we input different multiplications of the collected number of firebrands, which is 70 pieces, as our firebrand duration, and try to reproduce the experimental firebrand collection both in terms of mass and the number. So here you can see some snapshots of one of our simulation case. and how firebrands are generating, how trees covered with the fire, and some firebrands are moving upward with the convective column, and how firebrands are landing in the premises. So we do have this data, and we have that collection data. When we input 5 times of the collected number of firebrands as our firebrand duration, we could reasonably match the experimental firebrand collection. At that time, we could identify that firebrand should have a velocity around 2 meters per second, and the firebrand generation rate was calculated as 3.2 pieces per megawatt per second. So that number is related or in a form of heat release rate. So with that findings, we use that as an initial input for the next phase, which is modeling a prescribed forest fire experiment. So we did it in association with one of a management scale prescribed forest fire experiment done in Pineland National Reserve in New Jersey. So the dominant fuel is pitch pine. And Alex Philcop and his team, they participated in this great experiment. And they have collected the data of average fire intensity and location specified firebrand fluxes and environmental conditions, so on. So this is a satellite image of that burning plot, which has a 28 hectares an area, and they have initiated fire line from this line, and the fire is moving from left to right, aligned with the wind field. So we choose one region to include all the critical locations such as X, Y, Z collection centers, and the fire weather monitoring system, and the average location of the fire line, so on. And the thing that we know is we know the environmental conditions such as relative humidity, temperature, wind velocity, and the fuel load like understory fuel load and canopy fuel load, and the number of firebrands collected in this area and the time duration of firebrand collection. We know that data. But the thing that we don't know is how many firebrands generated from this fire line. Therefore, we wanted to model this in fire dynamic simulator, and we first obtained the developed wind field, as you can see here, because wind is really crucial for firebrand transport and deposition and so on. And then we processed the firebrand collection data used as our inputs in our model. Then we carried out an inverse analysis process, same as the experiment. So you can see one of the snapshots of one of our simulation, and firebrands are moving upward with the fire-induced buoyancy. So depending on the forces acting on these firebrands, such as their own weight, fire buoyancy, and the drag blow, their trajectories can be varied. And depending on that forces and depending on the trajectories, the landing location can be varied. And some firebrands are landing on the firebrand collection centers as well. Then we wanted to compare the experimental and simulation results for firebrand flux and the firebrand number density for the collection centers, which are Z, Y, and X. So we compare them for simulation and the experiment for firebrand flux and the number density against the size classes of firebrand. So as you can see here, both experiment and simulation results are reasonably matching each other. And at that time, we could identify the total firebrand injection rate is around 11,000 pieces per second. And the firebrand generation rate was found as around 4.2 pieces per megawatt per second. So this is a 23% increment greater than the single burning tree, because we are applying wind velocity and also we are applying a very high fire intensity in these cases. So we published these findings in Fire Journal, and if you're interested, you can go with this publication and get more idea about how we did and what are the findings that we obtained. Then we wanted to calibrate these firebrand generation rates to use in any other kind of a numerical model, because previously we found that firebrand generation rate for a specific vegetation species, which is pitch pine, and it was found for specific wind field or wind speed and fuel moisture content. If we want to use them in any other kind of a numerical model, we need to calibrate them according to the vegetation classification and the environmental conditions that we are focusing on. Since we are moving towards the appraising of Australian standard document, we wanted to do calibration according to the fire severities and the vegetation classifications given in this standard. So out of many, we selected forest scrubs and Malimuka vegetation classifications, which are really influential for firebrand generation. And the dominant forest are eucalyptus, banksia, and acacia. And then we wanted to calibrate them according to the severity of wildfires, which is explained in terms of fire danger index. So fire danger index is a numerical value and it's a function of wind speed, relative humidity, drought factor, and temperature. To obtain different fire danger indices, we control the wind speed while keeping other parameters as constant. So these fire danger indices actually give the idea about the severity of the wildfire. And we choose three of them, which are 100, 80, and 50, because to represent the very high intensive fire and the medium intensive fires. Then we calibrated them, taking as the fire generation rate that we found earlier as the base information. Then we wanted to use some other experimentalist data to find the effects of fuel moisture content and wind velocity and the species for firebrand generation. So Hudson and Barani, they have done a great experiments related to finding the effect of fuel moisture content and wind velocity for firebrand generation. We used their data and mathematically formulated these effects to apply on our firebrand generation calibration process. By doing so, we could identify the number of firebrands generated for certain fuel moisture content and different wind velocities, which are aligned with this Australian standard document. The next step was quantifying the firebrand attack on houses. In Australian, this is the important fact. In Australian standard document, they present the risk on the house in terms of the radiative heat flux. It's a quantitative value. And this standard tells us the firebrand attack also can be increased with the radiative heat flux, but it's a qualitative information. As I earlier mentioned, firebrand attack is crucial for structure ignition. Therefore, we need to make firebrand attack as a quantitative value to improve the quality of this standard. That's our objective. In this work, we are trying to make that firebrand attack as a quantitative value. First, we model different house designs, a single story and double story house, following the Australian standard house designs proposed by the government. So these houses have different strategic locations such as a gutter area, deck area, roof area, and understory, and the front side of the door. So these are the locations a lot of firebrands can accumulate and start an ignition. So we want to quantify how much firebrands land on these places and what's the possibility of starting an ignition. Then we place these houses according to the bushfire attack level given in this standard. So bushfire attack level is the scale of representing the radiative heat flux. For instance, bushfire attack level 40 means this house is receiving 40 kilowatt per square meter radiative heat flux depending on its location. So we position our model house at different bushfire attack levels and try to quantify the firebrand landing as well in correlation to the radiative heat flux. So we ran many simulations by varying fire danger index, bushfire attack level, vegetation classification, and different house patterns. First, we try to identify how much firebrand flux can be obtained for different house locations, such as roof area, gutter area, and deck area, so on. And we could identify some house locations, some strategic locations are received more firebrand flux compared to other locations, such as subflow area. So these locations are more exposed to the flow coming from the fire than the internal locations such as subflow area. And we can see, because of these findings, we can tell that these areas, these locations need some attention for constructing to withstand for high firebrand attack. And also we could see when we increase the fire danger index, in other words, when we increase the severity of wildfire, the firebrand landing flux also increase, which means the risk is increased. And also when we increase the bushfire attack level, in other words, when we are moving the house from towards the fire front, we can see a lot of firebrand flux can be, a lot of firebrands are landing on these locations. In other words, when the distance between house and the vegetation is very low, the risk is very high. Then we wanted to correlate this firebrand flux and the radiative heat flux to implement the Australian standard document. So according to our simulations, we try to plot them, and we could find that there's a logarithmic relationship between firebrand flux and the radiative heat flux for forest and scrub vegetation, while there's a linear relationship for Malimulga vegetation. So by doing that, right now we are at the stage of proposing these findings to Australian standard document S3959 to improve its quality to better counter the wildfire risk. So these findings were accepted in different conference, and some are presented as well. And as a summary, I can tell that first we quantify the firebrand duration rates for single burning tree. Then we move towards the firebrand duration of a forest fire. Then we try to calibrate that data with the fuel species, fuel moisture content, and wind speed. Finally, we quantify the firebrand attack on houses to improve the Australian standard document in correlation with different scales of wildfires and different vegetation species. So these are the basic findings that I can present for my PhD project right now. And thank you very much, and feel free to ask any question if you have.
Awesome. Yeah, thank you. That was your approach is a very interesting mix of kind of taking experimental data, doing semi-empirical thing, and then using FDS to you go kind of doing the full spectrum of all of the different approaches to this problem. It's interesting. We got a couple of questions in the chat box. The first is, using your simulation, does it mean that in a specific fire, you can quantitatively evaluate the effects of wind, fuel, or other elements on firebrand spotting?
Yes, the first case is we try to validate this model through one of a laboratory scale experiment and one of a field scale experiment, which means it gives kind of an idea that this model is working well, because we can reproduce that experimental and simulation results in a good agreement. Then we try to calibrate and these firebrand generation rates based on wind speeds and everything. And when we are developing the wind, we try to use eddy methods and wall of wind method, because to make it much more realism. And depending on that, we can mostly ensure that it's working well, and we can quantify their spotting and their landing flux and so on. Other subsequent parameters, yes.
I gotcha. Yeah. Another question here in the chat box is how did you determine the grid size, and what are the difficulties in simulating the actual firebrand?
Yes, that's a very great question, because we know when we're running this kind of a simulation, the results can be vary with the grid size. So we need to have a grid sensitivity analysis. We did it both in terms of qualitatively and using grid convergence index analysis. So we took parameters such as mass loss rate and heat release rate to find what is the convergence point of a grid, what is the optimum result that we can get. So the single burning tree, the grid size was 50 millimeters or 5 centimeters, and it's a quite a small resolution. And for the large scale forest fire, we got the grid resolution as 0.75 meters. So we continued that because all these things were done in correlation with the grid sensitivity analysis, and we can have a qualitative information that our results are converging. And what's the other part of the question?
What are the difficulties in simulating the firebrand?
Yes, so firebrands are inputting to these models as Lagrangian particles. So we didn't consider the pulses and the combustion of the firebrand during the flight. Because if we want to do that, then it may be a little bit tricky, because we need to have very fine grid resolutions. But here we are only focusing on the dynamics of the firebrand and their trajectories based on the flow around it, because the forces acting on it depends on the flow around it. So in this case, we don't want to have a much more grid resolution for like doing the deep in the fiber and combustion and pulses, that kind of things. So it was not much hard, but I don't say it was not easy as well.
Right. Yeah. No, that makes sense. That makes sense. This was a follow-up question to the first one. Is it possible to quantitatively evaluate which element has the greatest push effect on firebrand spotting in a specific fire?
Well, we can't say what is the most dominant factor for that. There are a lot of factors. For example, what we see was actually we put different sizes of firebrands, and we could see that when increased size, most of the firebrands are landing close to the fire line, and the firebrands which don't have a very big mass, a very big weight, they are moving far away. And depending on the shape, like cylindrical shape and cubic shape and spherical shape, the spotting distance can be varied, because the case is the drag glow act on the firebrands depends on the shapes and their sizes. So which means the resultant force acting on the firebrands can be varied with these parameters. In other words, it can be determined the spotting distance, because spotting distance can be varied with acting forces on the firebrands. So right now we are not at the stage of telling what is the crucial parameter for spotting, but we can say shape and size and their mass definitely influence for firebrand spotting and their landing distance.
Interesting. We have a hand up. Jason Sharples, would you like to ask your question?
Yeah, hi, thanks, Sarah, and thanks, Amila. Nice talk. I just had a question. I mean, when you were varying the forest fire danger index, you were only varying wind speed.
Yes.
I was just wondering, have you thought about, how do things change if you vary sort of temperature and relative humidity, because then that relates to fuel moisture content, and that might affect the number of embers that you actually have to launch as part of your Lagrangian tracing.
It's a great question. Actually, there can be a very good influential for fire danger index varying drought factor, relative humidity, and temperature, so on. So why we choose wind velocity over other parameters? Because the rate of change of wind is very rapid compared to other parameters. And also we know that firebrand can be really influential for firebrand transport can be really influential for wind velocity. And that's why we chose wind velocity. But depending on that wind velocity or wind speeds that we are taking, we try to find the optimum values for drought factor. So in this case, we use 10 to make it the worst case scenario. And we found the relative humidity, which is affect for the fuel moisture content, and we calculate the relative humidity based on the fuel moisture content. And from psychrometric charts, we choose the temperature as well. And as you said, there's a big influence for these parameters as well, but we didn't account them in this study. We only take account the wind speeds.
Thumbs up on that one. So we have a comment in the chat box here from Sam. Thanks you for the talk, and mentions that they have a new firebrand study where they looked at the characteristics of conifer trees combusting under a well-controlled wind field. It's published in Combustion Science and Technology, and he's got the link in the chat box there. So perhaps some more data to feed into your model there. So thanks
for that. Thank you very much, Sam. Yeah.
Okay, one final question. Got another one here. Would you mind sharing how you calibrated the effects of the vegetation species, changing the quantities, distances, or types in areas, and how do you actually did that?
That's one of a great question, and that's one part I was stuck for so long, because we don't have much more data. Because of the scarcity of data, we couldn't really find the effect of vegetation species. So I'll tell what I did. So we do have some experiments that done for different vegetation species and how firebrands generated from them. And I try to map that vegetation species to my focus vegetations. For example, Western juniper to pitch pine, like that. So when matching, I try to take account the vegetation height, their orientation of the tree leaves, and their canopy shape, so on. we don't have a really quantitative information to do that, but we did like in a qualitative way because of the scarcity of data. We don't have much more data, and that's a problem. And if we can have much more data, then it will be really good. We can do a very good research on that. Thank you for that question.
Yeah, that seems like a big challenge, is the lack of data there. We have a couple more minutes if there's questions for Ting as well. I'm sure we can get her back and ask questions. But yeah, thank you both for awesome talks. I mean, both very different topics, but great talks nonetheless. As we wrap up here, I will I'll give people a minute here to type if they're typing. But just let you know, we've got 2 more webinars left of the series, and then we're going to kind of wrap it up and start focusing on doing a workshop in person in Japan at the next IFSS meeting. So looking forward to actually seeing people again. So if there's no other questions, thank you guys again. And we'll see you next month. We'll get the speaker announcement out here and shortly. Thank you.